Let me begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class and just ask that you'd bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So, what I want to talk to you guys about today is the construction of what are known as differential forms. So I want to tell you, the differential forms differential formulation of calculus 3. All right. And so to start with, I have to tell you the basic ingredients here. And the basic ingredients are just the forms themselves. So we'll talk about the differential forms on R3. All right, so for R3, we build forms with basically dx, dy, and dz. Now, but even before we do that, we can talk about a zero form. So let me set the stage here. A zero form, it's just like f, which is, function on R3. So just a plain old real valued function is a zero form because it has zero differentials in it. All right. Then you can talk about a one form. A one form would be something like alpha, which would be like a dx plus b dy plus c dz. We call it a one form because it has one differential in it. And in each term that forms it, each term is formed with just one differential. Yes, sir? Well, we could think of integrals as the line integral is describing the integral of a one form. That is true. So, yeah. So here a, b, and c are functions. All right? So, definition, this is the work form that corresponds to the vector field. Well, let me just say it's the work form of the vector field ABC. All right? So there's a correspondence. You give me a vector field, I can give you a differential form, a differential one form. And here, omega as a mapping from vector fields to one forms, I refer to this as the work form correspondence. It's a one-to-one and an onto map. It's a bijective correspondence. It's also linear. If I had, if I added two vector fields, I would get them to one forms, and the one form which corresponded to the sum of the two vector fields would be the sum of the two forms, two one forms to which it corresponded. So that's a one form. An arbitrary one form looks like this. Now a two form, all right, two form, let's say beta. And by the way, the letters alpha and beta, they're not reserved. Like I don't just use alpha for one forms and beta for two forms. I typically use alpha, beta, gamma as sort of like arbitrary forms, all right? Anyway, so beta is something like a dy wedge dz plus b dz wedge dx plus c dx wedge dy. This is a two form because it's formed with the wedge product of two differentials, right? Now I showed you this wedge product before, right? We played with it in order to calculate Jacobian determinants for like a day, remember that? But now I'm just coming back to that and showing you we can do much more with it, actually. So this, by definition, is what's known as the flux form of the vector field ABC. So here phi itself is like a mapping from vector fields to two forms. And I refer to this as the flux form correspondence. All right. And, well, then there's one more step in this story, right? Three form. A three form looks, let's say gamma, would look like g times dx wedge dy. By the way, a, b, and c here are functions. G is a function, f is a function, all right? F, a, b, c, and g here are all functions, just real valued functions on R3. This is a three form, right? And that's it. See, because past that, if we were to try to write a four form on R3, we'd necessarily have a repeat of either dx with dx or dy with dy or dz with dz. We don't have four independent differentials. And so if we try to create a four form on R3, we just can't do it. This is the so-called top form. Yeah, this is an example of a top form. And I usually think of dx wedge dy wedge dz as, you know, the volume form on R3, all right? Quote unquote, the volume form. All right. So these are the players in the game, all right? And I want to do a calculation of the wedge product of two work forms, and let's see what happens, yeah? So, example 1, let's look at the wedge product of A and B's work forms. All right? So here we'll use like numbering, like A1, A2, you know, B1, B2, B3, the usual enumeration, if you will. And let's see here. So I've got, and I think it might be helpful for us to go to like dx1, dx2, dx3 notation for this example. I think the pattern will become more clear if I do that. So like, let's do that. So I've got a1 dx1 plus a2 dx2. I already regret this. a3 dx3. Oh well. b1 dx1 plus b2 dx2 plus b3 dx3. All right, great. Let's calculate this wedge product. So the way it works is just like normal, right? We got, I mean, I'll write it out in gory detail. I'm going to write it all out. A1, B1, dx1. There's going to be 9 things to write here. dx1, wedge dx1. Plus a1, b2. dx1, wedge dx2. Plus a1, b3. dx1, wedge dx3. Next line here, plus a2, b1, dx2, wedge dx1, plus a2, b2, dx2, wedge dx2, plus a2, b3, dx2, wedge dx3, plus a3, b1, dx3, wedge dx1, plus a3, b2, dx3, wedge dx2, plus a3b3, dx3, wedge dx3. Now, what I've just written here, I've written much more than I needed to, because 3 of those things are 0, right? Like dx1, so here's the basic rule is this, guys, is that dxi, like wedge dxj, is equal to minus dxj wedge dxi. Like that's baked into the cake of what we mean by the wedge product. It's anti-symmetric on the one forms, on the differentials. Basically, it's anti-symmetric on the differentials, and it extends linearly to higher products. That's essentially the definition of the wedge product. But so what this means then, of course, is like dx1, wedge dx1 is 0, dx2, wedge dx2 is 0, right? And dx3, wedge dx3 is 0 as well. Or if you like, you could go back to dx wedge dx, dy wedge dy, dz wedge dz is 0, right? In our other notation. So what I'm saying, this is 0, that's 0, this is 0, right? And I can group terms, right? I can group terms. So let me go back to the other let me go back to the xyz notation for a second here. Well, I guess I won't. Let me just think through this. dx2 wedge dx3. I'll keep those terms here. And then I want the terms with dx3 wedge dx1 there. And then I want the terms with dx1 wedge dx2, right? That's how I want to group terms. So you guys help me out here. What comes with the first one? Can you guys see it? Like I look for the 2, 3 terms. Where are they? Here, right? So that gives me A2, B3. And where else do I have one of those? Right here. But in order to get this, I have to, yeah, there's a minus, so I get minus A3, B2. Right? And then, let's see here. Next up, I'm looking for 3, 1. Where's 3, 1? Here it is, right? So I get A3, B1 minus A1, B3, right? Because the 1, 3 term had the dx1 wedge dx3. I have to turn that around, and that gives me a minus there, right? And then what's left is the 1, 2 terms, right? So I've got like this guy and that guy, which gives me A1, B2 minus A2, B1. Now, you should recognize this, right? What are we looking at? Cross product, right? This is exactly A cross B, the first component, right? This is A cross B, the second component. And this right over here, you got your third component of the cross product. So what do we have then? What is this all together? What are we looking at? In terms of the notation I've just introduced this morning, that is the flux form of what? Of the cross product, right? Is the flux form of the cross product. So, you know, we should probably keep this in mind for our future calculational purposes, right? The wedge product of 2 work forms is the flux form of the cross product, which means that this wedge product, it automatically calculates cross products for us in this sense. Yeah? Any questions? What is the wedge? That I can't answer. What is a form? Well, there are 0 forms, there were 1 forms, there are 2 forms, and there are 3 forms. Apparently, 1 forms and 2 forms correspond naturally to vector fields, right? So there's a chance maybe that I can, so like the whole project here is how can I rewrite the things we've done this semester using wedge products and forms in a nutshell. Like that's my goal today, is to show you how we can rewrite vector fields, cross products, dot products, the whole thing, using differential forms. So I've showed you at the moment that we can incorporate the cross product as a wedge product, right? What happens if we take, so, all right, so like proposition, we'll save this for later, you know, omega A wedge omega B is equal to the flux form of A cross B, right? Example 2, what happens if we take the wedge product of 3 things? What if we do omega A, wedge omega B? Actually, forget about omega. Let's say omega A wedge. Let's just do phi B. All right. So this would be like A1 I'm going to go back to, I'm going to use dx, dy, dz because like it's just less writing. A3 dz wedged with b. All right, so that's my b1 dy wedge dz plus b2 dz wedge dx plus b3 dx wedge dy. All right, so that's the flux form of b. There's the work form of a. We take the wedge product, what happens? I'm going to start writing a little bit less because there's lots of things that are 0, right? I mean, in principle, there's 9 terms here. But in practice, only 3 survive. See this? Like dx wedged with this one or wedged with this one, you either have like dx wedge dz wedge dx, which by the way is equal to minus dz wedge dx, but we know that dx wedge dx is 0, so this is equal to 0. So, yep.
So every time you flip like the dz or the dx, you just add a negative?
Correct. Yes, correct. Like this, it's this rule, dxi wedge dxj is minus gj wedge dxi. Just wherever you see it, you can use it. And also this operation's associative, so it doesn't matter like order of operations. You could either wedge the ones on the left first and the ones on the right second, or vice versa. Like it's totally associative. It's distributive. It's just not commutative, right? So that's why the wedge, I think, it's important to write. It's important to write the wedge because it reminds us that we're doing an abstract algebraic operation on this. In the same way that we don't just write AB and hope that the reader understands that, oh, that's the cross product. Right? We have a different notation for cross product and dot product to alert the reader to the fact that like the dot product of A and B is a scalar and the cross product of A and B is a vector, right? So here the wedge product is somehow going to incorporate all of that. So great. So these two terms are 0. So actually only the first one matters. And by the way, you can pull constants out too. That's another part of this. So A1, B1, I've got dx wedge dy, wedge dz, and for very similar reasons, a2, b2, right? a2, b2, and that one gives me dy, wedge, dz, wedge dx, right? And then I get a3, b3, dz, wedge dx, wedge dy. But what do you guys, if you look at this though, right? We can rewrite this as a1, b1 plus a2, b2 plus a3, b3. I mean, obviously the first one has dx wedge dy wedge dz. The question is, am I right to write this? Or like, should there be a minus? Let's think about this. I hear I'm right because there's 2 switches. Exactly. Now there's different ways to look at it. One way to look at it is I can take this dx and go hoppity, hoppity, 2 hops, right? And then I can take this dz here and go hoppity, hoppity, 2 hops. So it takes me 2 transpositions, 2 swaps of differentials to get from where I am to where I'm going. So minus a minus is a plus. And, does that make sense? What is that we're looking at?
Dot product.
Dot product, yes. So this is the dot product of the vectors a and b times the volume form, dx wedge dy wedge dz. So apparently the wedge product of a 2 form and a 3 form connects us, a 1 form and a 2 form connects us to a, the dot product of the corresponding vectors, right? It's easy to see that likewise, what would you have if I did like omega A, wedge omega B, wedge omega C, what would happen there? I mean, you could look at this as omega A, wedge the flux form of B cross C using our example 1, right? And then using example 2, we have A dot B cross C, don't we? We could go that way, couldn't we? But what else could you do? The wedge product's associative, yeah. So another way you could have processed this calculation, right, is you could have just as well gone, oh, but also omega A, wedge omega B, wedge omega C. Instead of collapsing the two omegas on the right, you could have done it on the left, right? I could have said, oh, that's really the flux form of A cross B wedged with omega C, right? And by the way, this is equal to the flux form of B wedged with the work form of A, because it's a general property that if you have an even form, a form built with an even number of wedge products, it commutes with all other forms under the wedge product. Because the process of like commuting it always takes you past an even number of differentials. So like it commutes, even forms commute with all other forms. And a two form's an even form. But anyway, so my point is that I know that this is equal to that, right? But by example 2, this is also equal to, A cross B dot C times, well, dx wedge dy wedge dz. Oh, look at that. So if you understand this, we've just learned that in particular A dot B cross C is equal to A C dot A cross B. Remember the dot product is commutative, right? I mean, we knew this already, right? Because we know that the triple product has this, we know about the cyclicity of the triple product, right? Remember that? Maybe you don't. But earlier in this course, we talked about the fact that the triple product calculates the volume of the parallelepiped, right? And that it has this cyclicity that you can write it, this is equal to that. And we can, there's one other that it's also equal to. My point is you could derive that with the wedge product like we just did. Yeah? That's not really my main point. I just stumbled into it, so I thought, why not while we're at it? So wedge product has got cross products, it's got dot products. But the other thing that's missing here, there's one other bit of algebra we have to talk about, which is what's called Hodge duality. Hodge duality concerns the fact that one forms and two forms are really connected. And so like Hodge duality is important. If you want to write formulas with differential forms, we need the Hodge dual in order to like write some of the best formulas. Now this might not matter for anything else I'm showing you today, but it will figure into future classes that I talk more about things. So let me just, it's a natural place to introduce the Hodge dual. So let me do that. So what the Hodge dual does in 3 dimensions is it always takes a P form star, it takes a P form and it gives you a n minus P, which in this case is 3 minus P form. All right, so here's how it works. The Hodge dual of the work form of A is equal to the flux form of A. That's Hodge duality. Hodge duality turns a 1 form into a 3 minus 1, which is a 2 form. And the Hodge dual of a 2 form, this is going to be really shocking, is a 1 form, because 3 minus 1 is 2. 3 minus 2 is 1. Good grief, what's wrong with me? So the Hodge dual of the flux form is the work form.
Is that asterisk like?
That's the Hodge dual, yeah. If you want, I could make it like a better looking, like one of those things. I don't know, but I'm just going to use asterisk because my stars degenerate. I mean, stars are degenerate. If anything, Hollywood has proved it's that. So, and then, of course, there's also the Hodge duality of the 0 forms and the 3 forms. So, like, what's the Hodge dual of just a 0 form, a function? It's got to be a 3 form. And which 3 form is it? It has to do with this f, right? So Hodge duality is linear. Like the Hodge dual of a sum is the sum of the Hodge duals. You can pull a constant out of the Hodge dual, right? It is a linear map. So the Hodge dual of f is just f times the volume form, dx wedge dy wedge dz. And the Hodge dual of like f times dx wedge dy wedge dz, what's that, you think? What's the Hodge dual of a 3 form? 0 form, right? It's got to be based on the coefficient function f. So the answer is just f. So this is Hodge duality. This is important if you want like a stone cold formula for dot product. How would you do that? Like, how would I, you know, A dot D in terms of like the wedge products and everything, how would I get that? It's what? If you think through this, this would be like the Hodge dual of like, oh no. Oh, let me not go down that path. Oh, why am I doing this? No. Brain broken. Let me stop. We don't need to go further than this at the moment. All right. Now today I'm focusing, okay, the Hodge duality actually becomes even more interesting when we shift over and don't just look at Cartesian coordinates and also look at like spherical or cylindrical coordinates for all this stuff. The Hodge duality picks up a new significance there. But I think that's all I have to say about that for the moment, so I'm going to stop there, as my spider sense is tingling that I should not chase the rabbit I was about to chase. All right, so that's algebra. All right? What comes after algebra? Trigonometry? Yeah, no, we're not going to do that. I don't know what trigonometry is here. That's actually an interesting question. What's trigonometry here? I don't know. It's a funny question. Did I just hear that, or did somebody say it? What's that? Yeah.
Would the flux form wedge the flux form exist in?
The flux form wedge the flux form is what? It's 0. Why? Because the flux form wedge the flux form is a 2 form wedge a 2 form, so it necessarily has a repeat of either dx, dy, or dz. It's inescapable.
And then what would the flux form look like? Flux form wedge the flux form in force space.
That would be a question for office hours. So, or maybe next class. But yeah, the flux form wedge the flux form could be non-zero in 4 dimensions. It's true, and that actually has significance to like electromagnetics, because in space-time there's a 2 form that corresponds to both the electric and magnetic field called the Faraday form, and actually we can write Maxwell's equations with the Faraday form as just one form equation. We can take 2 of Maxwell's equations and write them as one form equation. So the 4 Maxwell's equations I've showed you guys will translate into 2 differential form equations when we get there. So, anyway, so back on track. Calculus is what we should talk about next. So this is what's known as the exterior derivative. You actually already know the start of this. You already know what to do with the 0 form, right? What's the exterior derivative of a 0 form? df is the exterior derivative of a 0 form. This is the differential. You already know it. You already love it. Love it. Maybe that made it too big. That may have gone too far. Partial f partial x dx. Like if you had to choose between your mom or the concept of the differential of a function, you'd be like, sorry, mom. It was good for you to take care of me in my youth, but you know, I've grown up and I have to I love grown-up things. Sorry. Fortunately, there's a scriptural basis for not doing that, right? We have to honor our parents. Sorry, differential. But anyway, this is the exterior derivative of a zero form. It's just a one form. It's the differential. Can you think about how that plays together with the calculus we've learned this semester in my notation for today? Like, this is the work form of what? It's the work form of what vector field? This vector field, right? What is this vector field I'm writing? It has a name. What's that? Nablev. This is the gradient field, right? So the exterior derivative apparently tells us about the gradient, right? What happens then with the one form? How do we define the exterior derivative of a one form? So the answer is just like naturally, all right? So like, what's d alpha? And I'm saying alpha is like a dx plus b dy plus c dz like we did before. This marker's trash. Yeah, nothing but can. Let's see here. So dA wedge dx plus dB wedge dy plus dc wedge dz. In other words, the exterior derivative is simply defined on a form by saying you take the differential of the components of the form and wedge with the differentials that are already there. That's the definition of exterior derivative. It's the most natural thing in the world, actually. From a calculational perspective, you just do what you'd expect to do. Now, what is dA, dB, dc here? Well, those are differentials, right? So that's like partial x a dx plus partial y a dy plus partial z a dz. Wedged with dx. And this is a lot like the calculation I did in example 1, right? But now instead of just having, now we have derivatives, right? So like next up, we've got partial xb dx plus partial yb dy plus partial zb dz. All of that jazz there gets wedged with your dy. Right? So, just to be clear, this is dA, this is dB. So, all right. And then, of course, there's one more term, right? We got what? We got partial x, partial xc dx, partial yc dy, partial zc dz, wedged with dz. Now, there are 9 possible terms here, but only 6 survive, right? What are the survivors here? You got your dx wedge dy term. Excuse me, my bad. You've got your dy wedge dz term. You've got your dz wedge dx term. And then finally, you got your dx wedge dy term, right? And so if you look at that, what do we have here? All right, for yz, I've got, let's see here, yz, where's my, oh, this guy, right? So I've got partial, I guess I'll stick with this notation, partial y c minus partial z b. Then for the zx term, I've got partial zc minus partial xa And then finally, I've got partial xb minus partial ya. What are we looking at? Can you guys smell what I'm cooking here? What's that? A curl, right? This is if I let me say the vector field F is ABC for the sake of discussion. This is the curl of F. It's the first component of it. This is the second component of the curl of that F. And this right here is the third component of the curl. So what is this calculation? And by the way, what we're calculating is the exterior derivative of omega sub F, right? This is the work form corresponding to the vector field ABC. And we've showed that the exterior derivative of the work form corresponding to the vector field ABC is in fact the flux form of the curl of that vector field. In short, we've shown the following identity. We've shown that the exterior derivative of the work form of a vector field is the flux form of the curl of that vector field. So apparently exterior differentiation automatically builds in the curl. Yes, sir?
So does this mean that the exterior derivative of the exterior derivative of F is 0?
Yes, it does. And not just F, but any form. This is a general identity for the exterior calculus. D squared is 0 in general. Yep.
I think the middle blue term might be
Ah, did I do it wrong? Middle term's wrong. Partial z. I'm looking for the z wedge x. Yeah, you're probably right. Z, where's my zx? That's this guy, right? So, oh, that's just crazy. So, yeah, those are divergence terms. What's wrong with me? Good grief. I tell you what. Yeah, it should have been partial ZA, and then the down here, this is that comes with a dx wedge dz, which we got a flip flop, which gives us the minus partial xc. Thank you. Great question. The further down the board I go, the more suspect my calculations as a general rule. Right? You can have most confidence about whatever's written way up here. Right? Once we get past about right here, you gotta, I don't know. It's suspect. So yes, you're right, Jacob. Like generally speaking, it is a general identity of the exterior derivative. This can be proved, but not in here. That d of d alpha is equal to 0 for any p form. And this is something that's true not just in 3 dimensions, but in any dimensions. This is like a basic ingredient of the exterior calculus. Why am I calling it exterior derivative, by the way? What's that? There's a very simple reason. When we take the exterior derivative of one kind of form, it produces a different kind of form. See, I take the exterior derivative of a 0 form, and I get out a 1 form. I take the exterior derivative of a 1 form, and I get out a 2 form. Right? So it's type changing. We use this word exterior when something's like that. Right? This is also called the exterior algebra because the wedge product of 2 1 forms is no longer a 1 form. It's a 2 form, right? That's an exterior operation. That's why we use that word. What do you guys? There's one more derivative to do, right? One more derivative to do. Oh, but Jacob's got a good point. While we're here, what happens if we take the here, I'll do it here. So I think I'm going to suppose d squared equal to 0 is known, right? It can be shown in general. Then if we take the exterior derivative of f, this is the exterior derivative of the work form of the gradient, right? Which then is the flux form of the curl of the gradient. And you see, so if this is known, suppose that's known in general, and it can be shown in general, in fact, then this gives us an alternative way to prove, actually, the vector calculus identity that the curl of the gradient is 0. Yeah. Okay, so moving along here. What happens, so how's the two form going to go? What happens when we take the exterior derivative of the two form? The thing I'm erasing kind of foreshadows the calculation we're about to do. So here it is. So the exterior derivative of the, let's say, flux form of, let's say, f. All right, so we're taking the exterior derivative of f1 dx plus f2 dy plus f3 dz, right? And that's equal to df1 wedge dx plus df2 wedge dy plus df3 wedge dz. And I'm not going to write so much this time. I'm just going to write the part that matters. You think about it. As we calculate df1, df2, df3, what contributes non-trivially to the answer? Ooh, guys, don't let me do that. This is wrong. Duh. Man, what is, golly. Come on. I'm about to do the same calculation I just did. That would be dumb. I wanted to have a two form. The two form corresponding to the vector field f, which is not this. This is what? My apologies. It's f1 dy wedge dz plus f2 dz wedge dx plus f3 dx wedge dy. The pattern's just like the cross product, right, guys? So we've got df1 wedge dy wedge dz plus df2 wedge dz wedge dx, right? Plus df3 wedge dx wedge dy. So let's think about that. As we think about the differential of 1, 2, and 3, right? There's three terms in principle, but in practice, the only one that matters for the first one is like partial x f1, right? Do you see why?
Because when there's two the same, like dy wedge dy, that's equal.
That's right. When we have dy wedge dy or dz wedge dz, it's 0. So that's the only one that's not going to be 0 of the differential. Now, I could write it out if you want, but I've written a lot already. Let's see here. So this is going to be partial y f2 dy wedge dz wedge dx plus partial z f3 dz wedge dx wedge dy. The 6 things I'm not writing are all 0 because there's a repeated wedge in all of those terms. All right? Now we can factor out dx wedge dy wedge dz, right? Does it cost me any signs? Obviously, it doesn't cost any signs for the first term, right? Because it's dx wedge dy wedge dz. How about the second one? I can take this guy, right? Hoppity hoppity, two hops, right? This guy, hoppity hoppity, 2 hops, two switcheroos, and we get to the volume form. So in fact, we just sum the coefficients, right? So we've got like, I'll write it out. I'll splurge and write it this way. Partial f1 partial x plus partial f2 partial y plus partial f3 partial z. What is this? The divergence. Yes, the exterior derivative also calculates divergence. So apparently we have the following identity. The exterior derivative of the two form of a vector field is the divergence of that vector field times the volume form, dx wedge dy wedge dz. Now, if you believe me that d squared equals to 0 is a general identity of the exterior algebra, now we could use that to derive things that we, derived through more laborious means earlier this semester, I suppose, like d of d omega f, right? So like application. We know that 0 is equal to d squared. So like 0 is equal to d of d omega f, right? But d omega f is what? It's the flux form of the curl of f, right? But then by the calculation we just did, that's the what? The divergence of the curl of f. And by the way, the only way you can have, like, there's a cancellation property here. Whatever appears as the coefficient of dx wedge dy wedge dz, if that's equal to 0, that coefficient must be 0. So there you go. This is a derivation of the divergence of the curl being 0. Yeah.
So for the exterior derivative,
Uh-huh.
it seems to follow the same laws that were applied to its previous calculation with, let's say, omega wedge omega h.
Uh-huh.
It seems to follow the same laws, except instead of h, it has a nabla vector
Yeah.
that you mix it.
Right? I mean, I'm not... Are you comment or question?
Question, is that accurate?
Oh, is your comment correct? Is it like... I mean, what can you... Let me reformulate your comment, if you don't mind. What are the properties of the exterior derivative is really your question, right? Like, I've showed you how to calculate the exterior derivative of a 0 form, a 1 form, 2 form. What's the exterior derivative of a 3 form, by the way? It would have to be a 4 form, right? That's the way this works, is the exterior derivative gives you one more degree in the form degree. And there are no 4 forms, so the exterior derivative of a volume form is just 0. All right? So like properties of the exterior derivative. So here's one, the exterior derivative of like a constant times a form plus another form. You can pull the constant out and you have like this. So like the exterior derivative is linear. Okay? Like, yay. That is true. You can work that out. And I think but then here's the real interesting thing. The question you really want to ask is, what happens with a product? What's the exterior derivative of the wedge product of 2 forms? What do you guys think? Well, I'll tell you. It turns out it works like this. D alpha wedge beta plus minus 1 to the PQ alpha wedge d beta. Where here I'm supposing that the degree of alpha is equal to P and the degree of beta is equal to Q. Not like degree, I'm talking about form degree. So like the degree of a 1 form is 1, the degree of a 2 form is 2, the degree of a 3 form is 3. That's what I'm talking about. So the wedge product, the exterior derivative of a wedge product of 2 forms, it satisfies this graded product rule. It's called the graded product rule. Now, we could, if you know this, and this is something I proved this in the advanced calculus class, for example. It's not hard to prove. It's just not the point of this class. All right? You're like, well, this isn't the point of this class either. Fair enough, guilty as charged. But check this out. So there is a method to my madness. I'm actually going to show you something with all this that I hope you think is interesting. But I mean, I think this is actually very interesting. I've unified all of the different notions of differentiation we've looked at this semester in one uniform framework, right? I think that's kind of interesting, actually. So if we take the exterior derivative of the wedge product of two one-forms, if we know this, what happens? We get what? D omega f, right? Wedge omega g minus, because it's a one form, in a one form, minus 1 to the 1 times 1 is minus 1. So we get minus omega f wedge d omega g, right? And what is that? Well, we worked this out, right? What's the exterior derivative of this? Is what? This is the flux form of the curl of f, right? Wedged with omega g minus the work form of f wedged with the flux form of the curl of g. But now let us return to example 2. We can rewrite these in terms of dot products. Yes? So this is the curl of f dot g minus f dot the curl of g, all times dx wedge dy wedge dz. But you see, the flip side, if you allow me this short Mongo-style calculation, this is equal to the exterior derivative of the flux form of the cross product of f and g, right? Example 1. But this is the divergence of the curl of the cross product of f and g times the volume form. So what this shows us then is that the divergence of the cross product of two vector fields, this right here, is equal to this. So we could actually derive a multitude of product rules that we know for vector calculus as descending from the general product rule for forms. You might not care, but I think it's interesting. Whatever. All right, so let me move on. Any questions before yeah?
Is it true that the exterior derivative of n is equal to...
The exterior derivative of n? What do you mean by that? Let's stop you right there.
Let's say n is a p form. So then if the exterior derivative of n is the p form of wedged with the p with n.
You're asking me if a given form can be written as the exterior derivative of another form? Wedged with another form? Or like what? I'm not quite sure what you're... You probably tell me after class, Jacob. I'm not sure right offhand what to tell you about that. Maybe this would be helpful. I don't know. Definition: alpha is said to be exact on U, a subset of R3, if there exists phi such that alpha is equal to d phi on U. Does that remind you guys of anything? Like, let me translate this. Omega f, omega vector field f, is exact on U, a subset of R3, if there exists, phi such that omega sub f is equal to d phi, but that would be omega of the gradient of phi, right? Which is going to be true if and only if what? So there would be a natural correspondence between exact one forms and conservative vector fields. You could also, that's one definition to think about. Another one is alpha is closed. All right. On U subset of R3 if D alpha is equal to 0. So in the context of my vector, in the context of the example I was just giving you guys, so if we had, omega f closed, what would that mean? That would mean d of omega f, right? Which is the flux form of the curl of f is equal to 0. So it would be equivalent to the condition that the curl of the vector field be 0 on U. So the closed condition is that the curl is vanishing for the corresponding vector field. If we're talking about the one form, yeah.
So does that imply that if alpha is exact, alpha is also closed on the one form?
Well, the connection between closed and exact one forms and closed and exact forms is an interesting one. Certainly, it is true that exact alpha implies that alpha is equal to d phi, right? Which implies that d alpha is d of d phi, which I told you is a general identity is 0. So I think what you're just asking me was, does exact imply closed? That is true, exact does imply closed, but the converse is not generally true. It's not the case that every closed form is exact. However, if our space is simply connected, it is true that closed implies exact. But proving that for an arbitrary form is above our pay grade in here. But I do have a proof of it I show in the advanced calculus course, which isn't too hard. But anyway, so I was trying to get to integration, but you guys keep asking me interesting questions. This is short course and how we take the derivatives with forms. How about integration? Now you kind of already asked me about this at the start. Somebody asked me about Green's theorem. Aren't we already talking about integrals of forms in calculus 3? Well, yeah, actually, yeah, we are. And so like let me give you the cheat code. I'll give you the keys to the kingdom here in terms of integration. The answer is we integrate forms using all of the calculus 3 we've already learned. So like, what's that look like? What's the integral of a one form, for example? Right? The integral of a one form. So for us, this is a definition. The integral over a curve of the work form corresponding to a vector field is equal to the line integral of the vector field. That's it. And incidentally, that already comports with the notation we've used. See, because we already wrote that this is equal to the integral over the curve of like p dx plus q dy plus r dz, right? And notice that the work form corresponding to pqr is nothing more than p dx plus q dy plus r dz. So even the standard plain Jane calculus 3 textbooks already have how to integrate one forms. Now they probably don't think of it the way I'm thinking about it right now, but it's there. It's the same formula. So the integral of a one form we have to take over a curve. What do you guys think the integral over a surface of a two form of a vector field is going to be?